Oh, can you hear me?
Yeah, yeah.
Okay.
Okay. Well, it's 1:28, so we can wait another pause for another couple of minutes before we'll start. Do you want to maybe make it full screen?
Yeah, sure. It's better?
Yeah, yeah.
Okay.
Great.
Um,
Okay, maybe let's get started now. So our second speaker for this afternoon is Sayan Das from Colombia, and we'll be talking about large deviations for discrete beta-ensembles.
okay. Thanks for the introduction and thanks to all the organizer for organizing this event. So today I'm going to talk about large deviation for discrete beta ensembles. This is a joint work with Evgeny Dimitrov from Columbia as well. So my model is about discrete beta ensembles, but to motivate it, let me first talk about what is continuous beta ensembles. So continuous beta ensembles is a distribution in ordered particles on the real line. They are ordered, and its density is proportional to this quantity. You can think of like each particle is experiencing a potential individually, and they also interact according to this factor. And the motivation for studying this kind of measures comes from the random matrix theory. Indeed, these measures can be realized as measures for eigenvalues of random matrices for some cases, like when beta equals to 1, 2, or 4. These are the well-known orthogonal unitary and symplectic invariant matrices. And when V is quadratic, they are known as the Gaussian beta ensembles. So in these cases, they can be realized as eigenvalues for random matrices. So these are the continuous beta ensembles, and discrete beta ensembles is just a discretization of this guy. So a naive way or one way to discretize this model is just take LIs and set it to be like LIs are now living on the integers instead of real line and make it ordered. So these measures were considered by Johansson, but instead of this measure, we will consider a different kind of discretization. So we still have this potential V, but instead of this interaction factor is now given by this ratio of gamma functions like this. And not only that, the measures are now living on a shifted lattice. So I assume that the lambda i's are ordered integers and each li's are shifted by this factor. So they are not living on the same lattice if you vary theta. Okay. So this is my model and yeah. Okay. So yeah.
Z to only be positive integers, but in the real line, it's the whole real line.
Z.
Sorry, these measures live on the positive integers, right?
Yeah, positive
but
integers.
The original beta ensembles live on the whole real line, not on the positive real line.
That's true.
Why? That's the question.
Oh, so we can extend it to the whole real line as well, but we only consider the positive one because of the examples that we will consider later. Okay. So the first question you should ask, like, why is it even a discretization of the continuous one? So it is indeed a discretization. So if you look at this Carey ratio of gamma functions, the asymptotics will tell you like this actually behaves like this. So these two measures are indeed related by just beta equals to 2 theta. So they are the beta pops. And another questions you may ask, okay, so it's a discretization, but why do we care about this discretization? So although this was introduced very recently by Bourdin, Gorin, and Guionnet in 2017, it has appeared in special cases and several other models. So let me give you a non-exhaustive list of models where these measures appear. Perhaps the most heavily studied examples are the random losange and domino tilings, these measures. They also appear as measures on signatures and Young diagrams considered by Olshansky and Borodin and Olshansky. For this particular measure, you can even compute the proportionality constant and they are kind of related to the Selberg integral. But perhaps the most interesting fact is that this has some integrability structure given by Nekrasov equation. So what is Nekrasov equation? So basically, if you assume this potential to be analytic and some other extra feature, it gives you some kind of integrability. And you, okay, so I'm not telling you what is it, but it is very useful in computing fluctuations of these models. Okay, and no worries, we won't be using the Nekrasov equations. We will be relying on other assumptions. So yeah, so this discretization has been considered in literature. And yeah, so the kind of, so I so far I haven't really told you what is my V. The kind of V we will be considering is V will be continuous and differentiable, and they will have two conditions. The first one is a growth condition. This is quite natural because if you don't have such a condition, this won't be even summable, it won't be even a measure. And the next one is a condition on the derivative. Well, the increasing thing is fine, but I also allow some kind of this logarithmic behavior. Well, this just tells you that I can handle v for which the v prime behaves very badly near zero. So for example, I can have v to be x squared and x, and also this kind of v which has logarithmic singularity in the derivative. Yeah. So these are my assumptions, and we also deal with general assumptions, but let's just stick with this. So again, this is my model and this is my assumptions. Again, the model is living on this shifted lattice. Okay, so how to do analysis with this kind of measures? It turns out like these measures are actually very much connected to the potential theory. So if you believe me with this asymptotic behavior, Li minus Lj to the power 2 theta, and in the spirit of Gibbs measure, if you try to write it as exponential of something, the Hamiltonian will have this kind of behavior, a logarithmic interaction and an external potential. And this is known as the energy of the system. So this kind of things has been heavily studied in mathematical physics literature, and there are a lot of nice properties of this functional as long as you assume some v to be nice. So based on this intuitive figure, like probability is like exponential minus n squared times this, one can intuitively guess like what could be the limiting behavior of this kind of measures. So for example, if you consider the empirical distribution of the particles, scaled it by 1 over n, they will converge to some measure equilibrium measure. And this equilibrium measure is the unique minimizer of the functional that I showed you in the last slide. And they will be supported on 0 infinity because as Ramon mentioned, I am assuming that my measures is supported on the positive real line. And also I have this feature that the density is bounded by theta inverse. This is also easy to guess because of the shifted lattice, we have this kind of feature. The particles are separated by theta. That's why this condition pops up. And this result has been established in continuous case by this Benarus and Gioni paper and Benarus and Zetoni. And it has been done in other cases as well. I haven't really listed all the papers. And for the discrete beta ensemble case, it was derived by Brodin, Gorin, and Gioni in their paper. For the assumption that we deal with, we extended their result to our case. Okay, so the equilibrium measure actually exists. It is not a trivial fact why such a measure exists uniquely. It exists, and not only that, it has a density which is compactly supported. So typically, it looks like this. Either it will have like this, or it may have like some kind of saturated region where it is exactly theta inverse. So they will have an endpoint of the support, which I typically denote as BV. So let me now delve into the large deviation aspect of the largest particles. So since the rightmost point is BV, you kind of expect that the largest particle when rescaled should converge to BV. So it brings us the question, what about this probability of this event and this event, which are the large deviation event? What can you say about this events? So for the lower tail, so when L1 is atypically smaller than BV times n, the situation, if you look at the figure, is kind of like this. So BV minus y is here. You are telling all the particles are below this. In that case, all the measures that you can realize should be, density is still bounded between 0 and theta inverse, but they should be supported on this guy, right? You cannot exist this guy. So again, the functional is written here. What you should expect that The large deviation for the lower tail has this kind of rate function, and the rate is given by n squared. Okay, so this is for the lower tail. For the upper tail, the situation is you want the largest particle to exceed bv plus y, but you do not have any condition on the lowermost particles, so they are allowed to roam freely. Then what happens, it basically what the location of the largest particle matters, right? So if you define GV to be this, which you can think of like the potential of the largest particle. So V is the external potential, and this is the potential given by the presence of the other particles. So in ideal scenario, you expect the largest one to be near BV. So that's why you have BV. But in the large deviation scenario, you want your largest particle to exceed BV plus Y. That's why you have this guy. So this is the difference in the potentials of the largest particle, and the rate function is exactly this difference in potentials. However, the rate is now given by 1 over n. Okay. Yeah. The 1 over n essentially comes because we do not have any condition on the lower particles. They are allowed to roam freely, and only the largest particle roams. Okay. So since yeah, so the proofs are quite probabilistic. By that I means we do not use any integrability input like Nekrasov equation, which requires V to be analytic. So that's why we can deal with V which are continuous and differentiable, and that's it. Not only that, we can actually deal with those kind of potentials which are varying within Vn. We need some mild condition that Vn also converges to some limiting potential V. And one of the technical challenges in our proof is, remember, like the lattice are now shifted. So the usual techniques, it doesn't really hold up. We kind of need to have new probabilistic techniques to deal in our scenario. So as an application, we applied our results to this ensembles, Krauschuk ensembles, and some measures related to Jack function. In those two cases, we compute the explicit upper tail rate function. That means we computed the GV. And in both the cases, we show that the upper tail rate function has this asymptotic behavior. So this is kind of explicit. I haven't really written down, but this asymptotic behavior actually is quite, can be guessable from the Tracy-Widom GV distribution. Okay, yeah. So that's it.
Any questions for Sayan?
Since you don't use the Nekrasov equations, how much does it matter that you have these gamma function ratios? You know, if you've dealt with other types of versions of discrete beta ensembles, would you be able to do it, or more general functions there?
Yeah, so if we consider this kind of measures where there is just no gamma functions, we can still do it. And as long as we have some estimates like this behavior, I think we can still do it.
I guess your method probably also gives other large deviation sort of results for things, not just the location of the rightmost particle, but like the shape of the distribution, or are there other results you have like that?
By other results, you mean like something like large deviation of this kind? Yeah, so indeed in these two papers, they actually consider large deviation of the empirical distribution. But however, in the discrete case, because of some technical reasons, as the model are shifted, we do not have the exact large deviation of this guy. We have some kind of large deviation estimate, but not the exact rate function.
What's missing to be able to prove that?
I guess because of the technical reasons, we weren't quite able to get the exact rate functions, like the lower bound kind of things.
Okay, so you know one direction of it.
Yeah.
Okay.
So maybe a quick question. What about dynamic large deviation results? So, I mean, obviously there are natural dynamics on these discrete beta ensembles. Do you have some results for that?
Yeah, that's a good question. I do not know like for the general discrete beta ensembles, but we do have some results in specific cases like T-SIP and so on in the dynamic versions. Yeah, but it's a good question to ask about the dynamic large deviation of this discrete beta ensembles.
Thanks.
Any other questions? If not, let's thanks, Sayan, again.